So this is the sort of part which I found myself needing to design. I had a load of this stay flat hose. This is just to be able to cut off the end, of course, which I wanted to be able to connect to a British standard tap thread. And that led me down into the world of threads in SolidWorks. So let me share my screen and I will take you down the threads garden path, which this led me to. Okay, so we're going to design a simple nut as our object to cut our thread in. So I'm going to start with a simple hexagon. And just to make it fully defined, I'll make one of the edges horizontal, and then I'll set the distance of across the flats. And let's go for 40 millimeters. Go for 15 deep. We obviously want a hole in the middle, so we will cut a circle. Let's make that 25. Cut all the way through. So that's our basic representation of a nut. And often when I'm doing CAD modeling for nuts and bolts and things, I don't go a lot further than that because it's just representative of the thickness of the nut. You can keep your CAD models as simple as they need to be for the purpose you're going to put them to. But let's say we wanted to, in fact, the one other thing which is sometimes significant is the chamfer, and the easiest way, I think, to do that is to do a rotational sketch. So if we do a revolved cut, let's say we want to what have I done there? I'm not sure why that is not letting me draw. It's because I've selected the wrong plane for my. You just go back. Okay, let's make sure that it's not the front plane I want, it's the top plane. Make it nice and shallow. Make that collinear with the outside edge. And I can make that collinear with that plane. And let's have it just cut in a couple of mil. So I've defined a sketch that I'm going to use to trim my nut, and I'm going to rotate it around. Now I haven't put an axis in, so it's not going to let me finish that. I'm not sure the quickest way to deal with this, but what I do is I'm forced out of there. So the sketch is retained, but I've lost the operation, but that's not a problem because I can just jump back a step to put in the axis, which I want to be center of that circle. Now I can go back to my sketch, select my sketch, do my revolved cut. Now I can select my axis, and it's going to spin that all the way around there, give me a nice chamfered edge on my nut. And the last thing we want to do is make that symmetrical. Now, I didn't put in a central plane of symmetry before I started that. So what I normally do is go back and stick my reference geometry in before those features are defined. And now I can select the midpoint of 3 of these edges. And with that plane there, I can then mirror my revolve cut. There we go. So we've got what looks like a nut, and for cosmetic purposes, that's good enough. But if I want to actually put a physical thread in this, because as I was showing you at the start, I actually wanted to 3D print this, so a cosmetic kind of threaded surface isn't good enough. I want the actual real thread modeled in specific detail. Then I need a thread. I'm just going to save my document before I go any further. So the logical thing would be to go into insert features, and there is a threads feature. It's warning me not to use them for production quality threads, that the profiles provided are just kind of, I guess there's a kind of, don't trust these as being 100% perfect, but make the profile exactly what you want. And you can see from here, there's tap and die for whether you're cutting a thread into the inside or the a cylinder or the outside of a cylinder. We're cutting in the inside, so we would do a tap, so a metric tap, and then let's go for an M24 2. And then I need to select the edge of the cylinder that I want the thread to be cut through. And where do I want the thread to go to? I want it to go up to the other face. So I'll select the, select the box before I. Now you can say I want the thread to go a number of revolutions. You can see it's done that, goes part way through. If I say up to selection, then I need to select something, and then I'll select the other face, and job done. Really simple. Now my problem was that the thread that I wanted in my part was going to be a British standard tap thread. And in the threads menu, when I selected inch tap, I get all of these options, but none of them actually, it turned out, really equated to British Standard tap. I think the nearest was one of these. And I tried manually editing this this profile. That one's a 0.127, which isn't quite British Standard tap. Let's look up. It's not British Standard tap, it's British Standard pipe threads. I apologize. So got a Wikipedia, British Standard pipe threads. I was trying to do a 3/4 inch. So the thread density is 14 turns per inch. The pitch is 1.814, and you've got the major and minor diameters. So I should have been about 24.133 millimeters for my cut. Just wait for Solidworks. Solidworks seems to be not so happy with Zoom running, and it's taking ages to window switch. I'm going to restart it, see if it fixes it misbehaving. Okay, so that was the inner diameter for British Standard pipe for a 3/4 inch. And our thread profile for inch tap was one of the 14 turns per inch threads, the only one in this menu with 14 turns per inch is, that was two, there's that one. Just got the right pitch, and that all looks cosmetically about right. So I thought that would be fine, but when I 3D printed it, that did not work, didn't thread onto my standard tap adapter. So I had to resort to manually defining my thread without using the threads tool. Possibly my lack of knowledge rather than limitation of the threads tool, but it was a really useful exercise in learning some other ways to do things. So if I suppress that thread, and instead what we're going to do is we're going to use a swept cut. Now, a swept cut is where a sketch is moved along a path to define a cut. We've already used a revolved cut, where we revolve a sketch around an axis, but this time we're actually going to specify a path for the sketch to move along. So first thing we need to do is define a path that represents the pitch of our thread. And you find that on the curves menu. And there's all sorts of interesting things here, none of which I've ever used before. So these are maybe some more learning areas. But helix spiral is the one which I learnt about for this. And first of all, you need to specify an edge or a plane to sketch the circle on. So I can select this plane, the top of my nut, and then they want a sketch which is a circle to start the spiral from. And I've already got that because I've got this circle here, so I can just convert entities and I've instantly got a fully defined sketch. And when I exit, you can see that we're now in the spiral tool. So in this case, I need to put in the pitch rather than the turns per inch. And if we refer back to that Wikipedia page, the pitch of our British Standard pipe 3/4 inch thread is 1.814 millimeters. So we can put the pitch in, and we then need to say how many revolutions we want our thread to go through. So if I type in 10, you can see that's more than enough to go through the piece. So we can decide now, do we want our thread to actually kind of start in the, do we want our thread to go all the way through the nut, or do we want it to actually stop sort of just inside? And what I could do is, now that wasn't the way I wanted to do that because that's adjusted the pitch. So instead I could reduce the number of turns until it stops inside. I'll do that just because it's an interesting case to look at. So our thread's going to stop before it comes out the bottom of the nut there. So I've defined a spiral. Now I need a sketch to move along the spiral. And I found I had to define the sketch before I tried to define the swept cut feature. So I'm going to go to the sketch tab, create a new sketch. I'm going to put it on my top plane. And I essentially want a sketch which is a triangle, which is going to stick into the face of my piece of work. So make those horizontal. Now we have two dimensions that we care about here. If we just look back at our thread definition, there's the difference between the major and the minor diameters. So I could subtract one of those from the other. I have one which I actually prepared earlier. Which I'm just going to open in order to steal the dimensions off. So that ended up being 2.4 millimeters in my case, and 55 degrees was the angle of the cut. So the depth of my thread, 2.4 millimeters. Now this is where doing this manually, you've got some additional control. Because I wanted to 3D print this, I think I might have actually made this slightly deeper than it needed to be for a strict kind of thread definition, because when you 3D print, you find there's a little bit of expansion sometimes in the plastic compared to the dimensions you modeled. And I managed to fine tune this so that I could 3D print this, and the thread just worked without needing any finishing. And the other dimension we had there was this angle, which is 55 degrees. And then finally, of course, we want our threads to be in line with a linear was not the right mention there. It wasn't. I want, I think, to select the midpoint and that ring, and then I can say make them coincident. No, pierce. Pierce is the one we want. That's now fully defined, so I can exit my sketch. So I've got a triangle defined, which starts on that edge. I can now create my swept cut. So I need to specify the profile I want to sweep, which is my sketch. And I need to specify the path I want to sweep it along, which is my spiral. And what you can see is that it's gone a short distance and then ended. And the reason for that is that my spiral is starting in the wrong place. So you can see it's gone to the end of the spiral, which isn't very far away, in the wrong direction. I think I didn't have this problem before. I wonder if I can. Can I swap the direction? Yes, I can. There we go. So although my spiral started slightly further back, I think for this purpose, that is going to work just fine. So you can see that. Let's go to it's a bit difficult to make out what we've got. You can see the thread starting there and it spirals down in. And as we defined our revolutions to not quite come out the bottom, you can see our thread stops before the end. So in this case, if something's screwing into this, it would only screw in from the top and it would stop before it came out the bottom, because there's a kind of stop on the end of the thread there. You could, of course, put a draft on that to make it slope if you wanted to. What I did for my part was, before I defined my thread, I actually put a chamfer on this surface. think it's a millimetre. And that just enabled my thread to start cutting in. Doesn't look quite as neat as the one that I designed before, and for some reason it's not drawing the internal lines, but that's the principles of how I made the thread. Let's switch back to the one I actually 3D printed. You can see that I actually made a kind of bigger chamfer, so you can see where my thread starts to cut in. But at the scale of the 3D print, that was absolutely fine for that thread to go all the way through. And I didn't need to finish the bottom with a chamfer because I actually joined this onto another part, which I can show you. So I created this threaded nut part and I joined it onto the push fit connector that I designed separately. And that was the thing that I 3D printed in the end. And this thread 3D printed absolutely fine without any support material. So I designed this with sufficient tapers. I printed it this way up. So that was on the print bed, and so these overhangs were small enough that there was no support material needed. And so straight off the print bed, I ended up with a completely working thread and was able to connect my hoses up, and it worked very well.